Hey friends, it's good to be back with you. And today I'd like to talk to you about algorithms. This is a name we hear a lot, and you're going to use them a lot. What's an algorithm? Well, an algorithm in its most basic sense is just a set of mathematical operations that are described by some instruction. You follow the instruction, you get an answer. Now, that's not complete enough. There's good algorithms and there's bad algorithms. A good algorithm should have some distinct properties. The first of which is it should work. It should give you a correct answer. Another one is that it's well defined and easy to implement using a clear set of instructions. Another one is that it converges on the answer quickly. And the last one is that it will give you an estimate of how good your answer is, so that as you get an answer from your algorithm, you have some idea of what confidence you've got in it. Now, that's all pretty abstract. Let's maybe go through an example here of an algorithm. Now, let's say you want to find the root of an equation. Now, some lessons ago, we went through something called the bisection algorithm. That's an algorithm. But it wasn't very efficient. It absolutely did work, but it wasn't efficient. So let's go through maybe a better algorithm that does the same thing, but does it more efficiently. So let's do this. Let's draw our x and y axes like we always do. Okay, so there's x and there's y. And let's say I've got a function, okay, and it's, I don't know, f of x, I guess. And it looks like that, right? So pretty obvious right there is the root. Well, why don't we just plot it out and look for the root? Well, if the function's easy enough to evaluate, you can. But in general, functions are not easy to evaluate, and it's expensive to do this. It takes a lot of time, it takes a lot of computing power. So we need some other way to do this. Well, bisection worked. We would step forward until we crossed where the root was, and we'd iterate back and forth until we found it. It worked, not efficient. How about another one? Let's say we know the function, that's f of x, and we know its slope, we know its derivative. Well, we might know that one of two ways. We might actually know the closed form derivative, or we might be able to just do a finite difference estimate of it. Get a point, step forward a little bit, get another point, and then extrapolate, find the slope from there. But let's say we know f of x and f prime of x. Okay, so we know both of those. Let me fix that. There we go. So we know f of x and f prime of x, so we can find the slope at any point along with the function value. Well, we need a starting point. Now, many algorithms, I want to say most probably, need a starting point. Starting point in initial guess. Doesn't have to be very good, but there needs to be one. Well, let's just say we start right here. Okay, that's the initial guess. Well, doesn't have to be very good. This one isn't very good. Well, what would we do? Well, we're trying to find where this curve goes through 0. Well, we know it's a curve. We know it's not straight. But let's ignore that. Let's just plot a straight line anyway. Let's just go right there. And by the way, that's a one-term Taylor series approximation to the function. Well, how close are we? Not very. What we'll do now is we'll take this point. That was x0. This is x1. Well, what do we do there? Same thing. We just calculate right there. That's f of x1. And we're just going to find the slope again and do that. And that will be x2. Let me get out of your way here. And f of x2. See where this is going? Make it a one-term Taylor series approximation. We're going to estimate the root based on just assuming this curve is a straight line. Find the new value of f, make another curve, find another one, make another curve. And you can see that this is going to get closer and closer and closer as we progress. That'll be x3. So this algorithm, this procedure, has a lot of the properties we want. Number one, it's easy to implement. Okay? It doesn't require a ton of information. Like I say, if we don't have f prime of x, we can guess that using finite differences. It's relatively efficient. We can take big steps here at the beginning. It converges on the correct answer. It does. And we know how good an estimate we've got because we know how far apart these x's are. As x's get closer and closer and closer together, we know we're getting closer and closer to the root. Well, how close are you going to get? Well, this is a numerical calculation. Because of that, you're never going to get an exact answer. It's always going to be a finite approximation because computers work with finite precision. Well, with any estimate of a root, you get to the point where you don't care anymore. Once you get enough decimal places out, you really don't need more. And so every algorithm, when you're able to estimate how close you are to the right answer, will have some stopping condition, some exit criteria. And the exit criteria for this one might be when the successive x's are closer together than some value, it's time to stop. So, by the way, this is called Newton's method. It's a very common root finding algorithm. And it works well, works very well. It's implemented in a lot of software. So this is an example of an algorithm. Let's go to my computer now and let's do this exact same thing in MATLAB.